What if our universe had a bruise? A faint, cool mark left over from a gentle collision with another reality long ago. Imagine looking at the oldest picture of our cosmos, the very first light, and finding a fingerprint that doesn't belong to our world. Tonight, we journey to the edge of understanding, to a place in the sky known simply as the cold spot. It is a profound mystery, an anomaly so significant it challenges our most basic assumptions about the universe. Could this cosmic chill be a window, a portal, or a scar? As you settle in, let the questions fade and allow the story to unfold. We are about to explore the tantalizing possibility that the cold spot is our first, and perhaps only, glimpse into a parallel universe. To understand the significance of the cold spot, we must first travel back in time. Let us drift back 13.8 billion years to an era when the universe was an infant. In the moments after the Big Bang, the cosmos was a hot, dense, opaque fog of plasma. No stars, no galaxies, just a brilliant, searing glow. For about 380,000 years, light was trapped within this cosmic soup, unable to travel freely. But then the universe expanded and cooled enough for atoms to form, and at that precise moment, light was set free. This first light, this ancient echo of creation, has been traveling across the universe ever since. Today, it bathes everything in a faint, invisible microwave glow. We call it the cosmic microwave background, or the CMB. It is the oldest photograph of our universe, a baby picture of space-time. And when we look at it, we see something remarkable. It is almost perfectly uniform. The temperature of this background radiation is almost the exact same everywhere we look. A gentle 2.7 degrees above absolute zero. The tiny, minuscule variations in this temperature were the seeds of all structure, the places where galaxies would one day form. This uniformity is a cornerstone of our understanding of the cosmos, and that is why, when we find a place that is inexplicably, profoundly cold, it commands our complete attention. Let us begin our journey by truly immersing ourselves in the concept of this ancient light. The cosmic microwave background is not just a scientific data point. It is the oldest story ever told. Picture it as a vast celestial sphere surrounding us in every direction. It is a perfect, hollow globe of light, and we are at its very center. Every photon from this background that reaches our telescopes today has been on an uninterrupted journey since the dawn of time. It has traveled across billions of light years of expanding space, carrying with it a pristine memory of the universe when it was less than a millionth of its current age. The discovery of this radiation in the 1960s was a monumental moment in human history, a confirmation of the Big Bang theory that transformed cosmology from philosophical speculation into a precise science. It was discovered by accident as a persistent, gentle hiss in a radio antenna, a whisper from creation itself that refused to be silenced. This whisper tells us that the universe began in a state of incredible heat and density and has been expanding and cooling ever since. It is the ultimate evidence of our cosmic origins, a fossil light that connects our present moment directly to the beginning of everything. So as we proceed, remember that we are not just looking at data on a map. We are gazing upon the faint, residual warmth of the forge in which all of reality was created. Now, let us consider the near-perfect uniformity of this cosmic afterglow. Imagine a perfectly smooth, calm ocean stretching to an infinite horizon. The surface is almost entirely flat, but here and there you can see impossibly tiny ripples, variations in height that are almost too small to measure. These ripples in the cosmic microwave background are analogous to that. The temperature across the entire sky is astonishingly consistent, varying by only about 1 part in 100,000. This incredible smoothness tells us something profound about the very early universe. It suggests a period of hyper-rapid expansion, known as cosmic inflation, which stretched the universe from a subatomic size to a cosmic scale in a fraction of a second. This process would have smoothed out any initial wrinkles or imperfections, leaving behind the incredibly uniform canvas we see today. The tiny fluctuations that do exist, these minuscule hot and cold spots, are of paramount importance. They represent the seeds of cosmic structure. The slightly denser, slightly hotter regions had more gravity, and over billions of years, they pulled in more and more matter, eventually collapsing to form the first stars, the first galaxies, and the great cosmic web that we see today. Our very existence, the existence of our planet and our sun, can be traced back to one of these tiny, ancient seeds. The CMB is therefore a blueprint, a map of future creation, written in the language of temperature. The maps of this ancient light, created by space telescopes like the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck satellite, are among humanity's greatest scientific achievements. Imagine unfurling a map of the entire celestial sphere, flattened out into an oval shape. It is a stunning mosaic of color, usually depicted in shades of blue, red, and yellow. These colors do not represent what we would see with our eyes. They are a visual representation of temperature. The red and yellow patches are the infinitesimally warmer spots, the regions of slightly higher density that would eventually become clusters of galaxies. The blue patches are the ever so slightly cooler, less dense regions, which would evolve into the great cosmic voids. When you look at this map, you are seeing a snapshot of the universe on the grandest possible scale. It is a picture of the fundamental randomness that gave birth to order. The distribution of these spots appears, for the most part, entirely random, like the pattern of static on an old television screen. This randomness is exactly what our cosmological models predict. The laws of quantum physics, governing the universe at its birth, should produce a perfectly random Gaussian distribution of these temperature fluctuations. And for nearly the entire map, this holds true. It is a beautiful confirmation of our theories. But it is within this beautiful, predictable randomness that our mystery lies. Our focus now narrows. We scan across this beautiful, ancient map, our gaze drifting over the millions of tiny hot and cold fluctuations that pattern its surface. We drift past the region that will one day become our own Milky Way galaxy, a detail far too small to be resolved here. We glide over the seeds of the Virgo supercluster, the Laniakea supercluster, all just faint whispers in the data. Everything seems to be in its right place, a perfect symphony of cosmic chants. But then, in the direction of the constellation Eridanus, we find a note that is played out of tune. Our eyes are drawn to a patch on the map that is noticeably, undeniably different. It is a region of deep, profound blue. This is the cold spot. It is not just another one of the million tiny, cooler than average fluctuations. It is vast, spanning about 5 degrees on the sky, which is 10 times the size of the full moon. And it is not just slightly cool. It is significantly colder than its surroundings, a deviation from the average temperature that is statistically exceptionally unlikely to happen by pure chance. The probability of such a large and cold region appearing in the standard model of cosmology is estimated to be as low as 1 in 50, or perhaps even 1 in 1,000. It stands out on the map like a single, dark, mysterious island in a vast, temperate ocean. Let us try to visualize the scale and nature of this anomaly. Holding your hand up to the night sky, the full moon appears quite small. Now imagine an area that is 10 times wider than that moon. This is the apparent size of the cold spot. It is an immense patch of the distant sky. But its apparent size is deceptive because we are looking at a projection of something that is very, very far away on the edge of the observable universe. The actual physical size of this region, 13.8 billion years ago, was already immense, likely spanning hundreds of millions of light years. And what defines it is its temperature. While the average temperature of the CMB is 2.725 Kelvin, the center of the cold spot is about 70 microkelvin colder. This may sound like a tiny amount, but in the context of the CMB's incredible uniformity, it is a colossal deviation. Furthermore, it has a specific profile, a colder central region surrounded by a slightly warmer than average ring. It is a structured, organized anomaly in a sea of predicted chaos. This structure makes it even more difficult to explain as a simple, random fluke of nature. It begs for an explanation. It is a feature that does not quite fit the elegant picture painted by our standard cosmological model. It is a loose thread in the cosmic tapestry, and pulling on it could unravel everything we thought we knew. So, what could create such a vast and unusually cold region in the primordial light of the universe? The first and most straightforward hypothesis does not involve new physics or other dimensions. It involves looking for something, or rather, a lack of something, in the space between us and the cosmic microwave background. The leading conventional explanation is the existence of a supervoid. Imagine the universe as a cosmic sponge, full of dense filaments of galaxies and great empty voids in between. A supervoid is the largest of these empty regions, a truly gargantuan bubble of near-nothingness. The Eridanus supervoid, as it is sometimes called, is a hypothesized structure located in the same direction as the cold spot, but much closer to us, roughly 3 billion light years away. The idea is that this supervoid is not the source of the cold itself, but that it creates the cold spot as an illusion, a trick of cosmic perspective. It is a gravitational effect that leaves its imprint on the light passing through it. This explanation is grounded and elegant, using the known laws of physics to account for the mystery. It suggests that the answer lies not at the beginning of time, but in the vast, dark emptiness of the intervening space. To understand how a void could make light appear colder, we must consider the journey of that light through an expanding universe. This is a concept known as the integrated Sachs-Wolf effect, As a photon of light from the CMB begins to enter a supervoid, it falls into a gravitational well. It's not a well made of matter, but a well made of a lack of matter. As it falls in, it gains energy, and its wavelength becomes shorter, a process known as a gravitational blue shift. It becomes, for a moment, slightly hotter. Then, the photon travels across the immense expanse of the void, a journey that might take 1 billion years. During this time, the universe continues to expand. The void itself stretches and becomes shallower. When the photon finally climbs out of the other side of the gravitational well, it loses energy, a process called a gravitational redshift. However, because the universe has expanded while the photon was inside, the hill it has to climb on the way out is less steep than the one it fell down on the way in. Therefore, it loses slightly less energy climbing out than it gained falling in. The net result should be that the photon emerges slightly more energetic, slightly hotter. This is the normal Sachs-Wolf effect. But in a universe dominated by dark energy, the expansion is accelerating. This acceleration stretches the supervoid even more dramatically while the photon is inside, making the gravitational well even shallower on its exit. This enhanced effect means the photon loses more energy than it gains, and it emerges slightly cooler, slightly redder than when it entered. A supervoid in an accelerating universe should leave a cold imprint on the CMB light passing through it. This supervoid explanation is, for many cosmologists, the most plausible answer. It is Occam's razor in action. The simplest explanation that fits the facts is often the best. It requires no new physics, no exotic entities. It relies only on gravity, general relativity, and the known components of our universe, including dark energy. Following this line of reasoning, astronomers began to hunt for this colossal void. They conducted deep sky surveys, meticulously mapping the distribution of galaxies in that specific direction of the sky. The task is monumental. Counting and measuring the distances to hundreds of thousands of galaxies over a vast volume of space is a painstaking process. The goal was to find a region that was significantly underdense, a place with far fewer galaxies than the cosmic average, a void large enough and empty enough to produce the observed coldness through the integrated Sachs-Wolf effect. For a time, this search seemed promising. Early surveys did indeed find evidence of a large, underdense region in the direction of the cold spot. It appeared that the mystery might be on the verge of being solved, that the explanation was indeed a grand, empty cathedral in the cosmic architecture, playing tricks with the ancient light passing through its silent halls. However, as our observational capabilities improved and our surveys became more detailed, a problem began to emerge with the supervoid hypothesis. While surveys have confirmed the existence of a large, underdense region in the direction of the cold spot, it appears this void is not nearly super enough to account for the entire anomaly. The observed void is more like a collection of smaller voids, a somewhat sparse region, but not the single, gargantuan, profoundly empty chasm that the theory requires. The calculations suggest that the void we have found can only explain a small fraction of the observed coldness, perhaps only about 10 to 20% of it. It creates a small cooling effect, but it falls far short of explaining the deep, profound chill that makes the cold spot so unique. This has left the scientific community in a state of gentle puzzlement. The simplest explanation, the most elegant and conventional one, seems to be insufficient. The data does not quite line up with the theory. This discrepancy, this gap between what the void can do and what we actually see, is what keeps the mystery alive. It forces us to keep searching, to look beyond the comfortable and the known, and to consider possibilities that are far more strange. The shortfall of the supervoid model means that something else must be contributing to the coldness. Perhaps there is another, larger void that we have not yet detected. Or perhaps the integrated Sachs-Wolf effect is not fully understood. But it also opens the door to more exotic, more mind-bending explanations. It allows us to ask a profound question. What if the cold spot is not an illusion created by intervening structure, but is in fact an intrinsic feature of the cosmic microwave background itself? What if that region of the universe was genuinely colder from the very beginning? If that is the case, we would need a new mechanism, something not included in our standard model of cosmology, to create such a feature. This is where the narrative takes a turn from the observable to the theoretical, from the cosmos we know to the multiverse we can only imagine. The failure of the simple explanation forces us to confront the truly strange, to entertain ideas that exist at the very edge of physics and philosophy. The cold spot ceases to be just a data point and becomes a potential clue to a much, much larger reality. And so we arrive at the most speculative, the most awe-inspiring, and perhaps the most beautiful explanation for the cold spot: the multiverse hypothesis. This is not a single theory, but a collection of ideas that stem from different branches of theoretical physics, including string theory and eternal inflation. The core idea is that our universe is not unique. It is but one bubble, one island in a vast, perhaps infinite, cosmic ocean filled with other universes. This grander reality is often called the multiverse. In some of these models, new universes are constantly being born in a process called eternal inflation. Imagine a cosmic foam with bubbles of space-time popping into existence, each one expanding to become a universe in its own right. Each of these bubble universes could have its own unique set of physical laws, its own fundamental constants, its own number of dimensions. Most would be sterile, inhospitable to life as we know it. But in this infinite foam, by sheer chance, bubbles like ours, with the perfect conditions for stars, galaxies, and life, would inevitably form. It is a staggering concept that reframes our entire existence, demoting our entire cosmos from the universe to just a universe. Within this framework of a cosmic foam of bubble universes, the theory of a cosmic collision emerges. What if, in the very distant past, when our own universe was incredibly young and small, another bubble universe drifted too close? What if they gently bumped into each other? The collision would not have been a cataclysmic explosion in the way we might imagine. It would have been a quantum event on a cosmic scale, a disturbance in the very fabric of space-time. The interaction would have sent ripples of energy through our infant universe. Proponents of this theory, such as physicist Laura Mersini Houghton, have calculated what the signature of such an event would look like on our cosmic microwave background. The collision would have effectively pushed energy out of a vast region of our universe, creating a large-scale perturbation. This perturbation, this cosmic bruise, would manifest today as a gigantic region on the CMB that is colder than its surroundings, with a very specific temperature profile. It would be a scar left on our universe, a permanent reminder of an encounter with a neighbor from another reality. It is a theory that is both breathtakingly audacious and, in its own way, deeply compelling. The predictions made by this multiverse collision model are startlingly specific. The theory doesn't just predict a cold spot, it predicts its size, its temperature profile, and even other, more subtle statistical anomalies in the CMB. Some proponents of the theory claim that the observed features of the cold spot match their predictions with remarkable accuracy. They point to the specific shape of the spot, its cold center, and slightly warm surrounding ring, as evidence that fits the collision model better than it fits the random chance model. Furthermore, the theory also made predictions about other, smaller scale anomalies that were later found in the Planck satellite data. It is a theory that is, at least in principle, testable. If we could find other, similar spots on the CMB, or confirm other statistical predictions of the model, the evidence for a cosmic collision would grow stronger. It remains a highly contentious and speculative idea within the scientific community, but it is one that cannot be easily dismissed because it seems to explain the observed data in a way that the standard model cannot. It presents a tantalizing possibility that we are looking at the fossilized evidence of an event that took place before the birth of the first stars, an event that connects us to a reality beyond our own. Let us take a moment to truly contemplate what this would mean. If the cold spot is indeed a cosmic bruise, it would be the first observational evidence for the existence of other universes. It would transform the multiverse from a mathematical curiosity, a philosophical toy, into a scientific reality. It would mean that the vast, sprawling cosmos we see, with its hundreds of billions of galaxies, is just a tiny fraction of what truly exists. Our reality would be but one chapter in an infinite library of cosmic stories. This realization would be a philosophical shift on par with the Copernican revolution, which moved the Earth from the center of the universe, or the discovery of exoplanets, which showed us our sun is not unique. It would be the next great step in our cosmic humbling, a profound reminder of our place in the grand scheme of things. The cold spot would no longer be a mere anomaly, but a sacred place on the sky, a tangible link to the unimaginable. It would be a window, not made of glass, but of temperature, through which we could peer and catch a fleeting glimpse of the true magnificent scale of existence. Of course, this extraordinary claim requires extraordinary evidence, and at present, the evidence is far from conclusive. The supervoid explanation, while imperfect, has not been definitively ruled out. It is possible that our surveys have simply missed the true extent of the void, or that our understanding of its gravitational effects is incomplete. Many cosmologists remain deeply skeptical of the multiverse interpretation, viewing it as an unnecessary leap into speculative physics when a more mundane explanation might still be found. Science, in its careful and methodical way, must exhaust all conventional possibilities before embracing the revolutionary. The debate between these two interpretations, the cosmic void versus the cosmic bruise, represents a fascinating frontier in modern cosmology. It is a place where the limits of our observational power meet the boundaries of our theoretical imagination. The cold spot sits right at this intersection, a silent arbiter in a debate about the fundamental nature of reality. And until we have more data, more powerful telescopes, and better models, it will likely remain an enigma, a beautiful and unsettling question mark painted across the dawn of time. Let's return to the idea of the supervoid and give it its due respect. Even if it is not the full explanation, the Eridana supervoid is a magnificent object in its own right. We are talking about a region of space that is possibly 1.8 billion light years in diameter. It would be, by far, the largest structure ever discovered by humanity. To try and comprehend this scale is almost impossible. Our own Milky Way galaxy is about 100,000 light years across. This void is thousands of times larger. If our galaxy were at its center, the nearest other major galaxy would be hundreds of millions of light years away. The night sky from a planet within this void would be a place of profound and absolute darkness, with only the faint, distant smudges of the most distant galaxies visible to the most powerful telescopes. It is a place where the universe's expansion has triumphed over gravity almost completely, sweeping the region clean of matter. The study of such voids is crucial to understanding the large-scale structure of the cosmos and the mysterious push of dark energy. So, whether it is the cause of the cold spot or not, the search for it has revealed the existence of a cosmic architecture of unimaginable emptiness and scale. Now let us place ourselves inside that void for a moment. Imagine floating in the center of this immense emptiness. In every direction, there is almost nothing. The silence is not just an absence of sound, but an absence of substance. The gravitational pull is almost non-existent. You are in a cosmic desert, a place of deep and abiding calm. The photons of the cosmic microwave background stream past you, as they do everywhere in the universe. But here, their journey is unique. As they pass through this vast, underdense region, they are subtly changed. The accelerating expansion of the universe, driven by dark energy, stretches their wavelengths just a little bit more here than anywhere else. It is a place where the fundamental tension of the cosmos, the pull of gravity versus the push of dark energy, is laid bare, with dark energy as the clear victor. It is a laboratory for studying the future of our universe, a glimpse into the big freeze or heat death that may be our ultimate fate, when all galaxies have expanded so far apart that the universe becomes a cold, dark, and empty place. The supervoid is not just an object, it is a prophecy, a vision of the cosmic future, existing right here in our present. Contrast this with the imagery of the cosmic collision. Here, the story is not one of emptiness, but of contact. It is a story of connection, of our universe being part of a larger family, a larger system. The cold spot in this view is a memory. It is a mark of our cosmic heritage. It suggests that the initial conditions of our universe were not set in isolation, but we're influenced by its environment, by its neighbors in the multiverse. This idea resonates with a deep human intuition that we are not alone. While we often think of this in terms of extraterrestrial life, the multiverse concept takes it to an entirely different level. It suggests that entire realities exist parallel to our own. The thought that we could have tangible, physical evidence of such a reality is what makes this theory so captivating. It feels less like a cold, abstract theory and more like the opening chapter of a grand, cosmic myth. It is a story of origins that is both scientifically grounded in complex physics and deeply resonant with our sense of wonder. Think about the implications for the laws of physics. If other universes exist, do they have the same laws as ours? String theory suggests that there could be a vast landscape of possible physical laws, perhaps 10 to the power of 500 different sets of rules. Our universe just happens to have the specific combination of constants that allows for complexity and life to emerge. This is sometimes called the anthropic principle, the idea that the universe appears fine-tuned for our existence. Because if it were any different, we wouldn't be here to observe it. The multiverse provides a natural explanation for this fine-tuning. If you have an infinite number of universes, it is no longer surprising that at least one, by pure chance, has the right conditions for life. The cold spot, if it is a sign of the multiverse, would be our first piece of evidence supporting this incredible picture. It would suggest that the laws of nature as we know them are not fundamental, but are more like local bylaws, specific to our own cosmic neighborhood. The true, fundamental laws would be those that govern the multiverse itself, the meta-laws that give birth to all possible universes. There are other, more subtle clues in the cosmic microwave background that some scientists point to as potential evidence for theories beyond the standard model. For instance, there are strange alignments in the largest scale fluctuations, sometimes referred to as the axis of evil, because they seem to align with the plane of our own solar system, a coincidence that should not exist. There are statistical anomalies, differences in the fluctuations between the two hemispheres of the CM-BA sky. The cold spot is the most famous and robust of these anomalies, but it is not entirely alone. It is part of a collection of small, nagging inconsistencies that suggest our picture of the universe might be too simple. Each of these anomalies could be a statistical fluke, a 1 in 100 chance that just happened to occur. But taken together, they begin to paint a picture of a cosmos that is slightly stranger, slightly more mysterious than our theories would predict. The cold spot is the flagship of this fleet of cosmic mysteries, leading the charge into the unknown. Let us consider the future of this research. How will we ever solve this mystery? The answer lies in more precise data. Future CMB telescopes, both on the ground and in space, will map the ancient light with even greater resolution and sensitivity. They will be able to study the polarization of the light, which contains a wealth of additional information about the early universe. At the same time, massive galaxy surveys, like the upcoming Vera C. Rubin Observatory, will map the three-dimensional structure of the universe with unprecedented detail. These surveys will be able to definitively confirm or deny the existence of a supervoid capable of creating the cold spot. They will provide the final word on the conventional explanation. If a sufficiently large and empty void is found, the mystery will be largely solved. But if it is not, if the discrepancy remains after these new, ultra-precise maps are made, then the case for new physics, and perhaps for the multiverse, will become dramatically stronger. We are living in a golden age of cosmology, where we are on the cusp of being able to answer some of these truly fundamental questions. The cold spot also serves as a beautiful example of how science works. It is a story of observation, theory, and debate. An anomaly is detected in the data. A simple, conventional explanation is proposed. More data is gathered, and the simple explanation is found to be lacking. This opens the door for more creative, more exotic ideas. These new ideas then make new predictions, which can be tested with further observations. It is a slow, careful, and sometimes frustrating process, but it is how our knowledge progresses. The cold spot is a perfect focal point for this process. It is a well-defined problem, a specific question that we can address with concrete measurements. It is a mystery that is currently unsolved, which makes it exciting. It reminds us that science is not a finished book of facts, but an ongoing journey of discovery. There are still great, unexplored territories in our understanding of the cosmos, and the cold spot is a clear signpost pointing towards one of them. Let us drift back into a more meditative state now, leaving the scientific debate behind. Let us simply float in the presence of this cosmic mystery. Picture the map of the CMB again in your mind's eye. See its beautiful, intricate pattern of warm and cool tones. And then, see the deep blue of the cold spot. Do not think of it as a problem to be solved, but as an object of contemplation. What does it feel like to gaze upon a feature that may have been created by contact with another world? It is a feeling of profound awe, a sense of connection to something immeasurably vast. It is a humbling experience, a reminder that our human perspective is so limited. We are like ants on the surface of a great painting, able to see only the tiny cracks and pigments directly in front of us, while the grand design of the artist remains beyond our comprehension. The cold spot is a hint of that grand design. It is a whisper from the artist, a clue left for us to find. The two competing explanations for the cold spot offer two very different ways of feeling about the universe. The supervoid theory speaks of a universe of immense scale, of vast emptiness and majestic, cold architecture. It is a universe governed by understandable, if complex, physical laws. It is a universe we can, in time, come to know and map. It evokes a sense of solitude, of our place within a single, magnificent, but ultimately lonely cosmos. It is the beauty of a vast, silent desert. The multiverse theory, on the other hand, speaks of a universe of infinite possibility, of connection, and of unimaginable variety. It suggests a cosmos that is not lonely, but is teeming with other realities, other stories unfolding in parallel to our own. It evokes a sense of wonder, of being part of an infinite, interconnected family of worlds. It is the beauty of a vast, vibrant, and unseen ocean. Both visions are beautiful. Both are awe-inspiring. And the cold spot sits at the balance point between them, allowing us to contemplate both possibilities at once. As you continue to relax, as your breathing becomes deeper and slower, allow your mind to drift freely between these two ideas. First, imagine yourself floating at the edge of the great Eridanus supervoid. Feel the deep, profound emptiness around you. Sense the pull of dark energy gently stretching the space you inhabit. Watch the ancient photons of the CMB stream past, their energy slightly depleted by their long journey through this nothingness. Feel the immense, quiet peace of this cosmic desert. There is no judgment here, no rush, only the slow, inexorable march of cosmic time. The coldness is not harsh, but gentle and serene. It is the quiet of a universe at rest. Allow this feeling of serene emptiness to wash over you, clearing your mind of all thoughts, all worries. Let yourself become one with the quiet and the dark. Now shift your perspective. Imagine our universe as a single, shimmering bubble. It is warm and bright inside, filled with the light of 100 billion galaxies. All around it, in a space beyond space, are other bubbles, an infinite foam of other worlds. And now you see another bubble slowly drifting towards ours. They touch. There is no sound, but you feel a gentle ripple spread through the fabric of our reality. A wave of energy passes through our infant cosmos, leaving behind a permanent mark, a memory of the encounter. This is the cold spot. It is not a sign of emptiness, but a sign of connection. It is proof that we are not alone in the grandest sense of the word. Feel the sense of wonder and possibility that this idea brings. The universe is not a closed, isolated system. It is part of a grander, more dynamic, and more mysterious whole. Allow this feeling of infinite possibility to fill you. The sense that reality is far larger and more magical than we can possibly imagine. Let this sense of wonder carry you deeper into a state of peace. Regardless of its true nature, the cold spot serves a powerful purpose for us tonight. It is an anchor for our imagination. It is a focal point for our journey away from the concerns of the everyday and into the profound tranquility of the cosmos. By contemplating its immense scale and its deep mystery, we naturally recalibrate our own sense of perspective. Our own problems, our own anxieties, seem to shrink in comparison to a question about the very nature of reality itself. The coldness of the spot is not something to be feared, but something to be embraced. It is a cosmic cool compress for a weary mind. It is a reminder of the vast, silent, and peaceful spaces that exist, both outside of us in the cosmos and within us in the quiet depths of our own consciousness. It is a doorway to stillness. As you gaze upon it in your mind's eye, feel the stillness of deep space begin to permeate your being. The constellation in which the spot resides, Eridanus, is named after a mythical river. This is a beautiful piece of cosmic poetry. For centuries, humans have looked up at this region of the sky and seen a flowing river. And now, modern science has found a river of a different kind, a river of cosmic cold, a stream of photons carrying a mysterious, chilly secret from the dawn of time. Or perhaps a river that marks the boundary between our universe and another. Like a great river, the mystery of the cold spot flows onward, carrying our questions with it into the future. We may never know the definitive answer in our lifetimes, and that is perfectly all right. The value is not just in the answer, but in the journey of asking the question. It is the act of looking up, of wondering, of allowing ourselves to be humbled by the scale and beauty of the universe that brings us peace. The cold spot is an invitation to do just that. As we near the end of our exploration, let the two images, the vast, empty void and the gentle, cosmic collision, merge in your mind. Perhaps the truth lies somewhere in between, or is something else entirely that we cannot yet conceive. The beauty of the mystery is that it holds all possibilities at once. It is a quantum state of explanation, both a void and a bruise, until a future observation collapses the waveform. And so, we can hold both realities in our mind at the same time. We can appreciate the serene emptiness of the void and the profound connection of the multiverse. We can let the cold spot be a symbol of the great unknown, a testament to the fact that the universe will always be more mysterious and more wonderful than our current theories can contain. It is a permanent reminder to stay curious, to keep exploring, and to always look up at the night sky with a sense of awe and wonder. For it is in that sense of wonder that we find our deepest connection to the cosmos and our most profound sense of inner peace. So, as you finally let go and prepare to drift into sleep, hold the image of the cold spot one last time. See it as a cool, blue, peaceful island in the warm glow of the early universe. It is a place of quiet, a place of mystery, a place of calm. Whether it is a window into a vast emptiness or a window into another world, it is, for you tonight, a window into deep and restful sleep. Let its cosmic chill soothe you. Let its grand scale comfort you. And let its profound mystery remind you that you are part of something indescribably vast, ancient, and beautiful. You are a child of the cosmos, made of stardust, living in a universe that is still revealing its greatest secrets. And now it is time to rest, to float gently in the cosmic river, and to let the current carry you into the peaceful void of your dreams. We have journeyed together to the very edge of the observable universe and gazed upon one of its most profound enigmas. We've explored the two leading ideas for the cold spot: the magnificent, empty cathedral of a supervoid, which would create the coldness through a trick of gravitational light, and the breathtaking theory of a cosmic collision, a gentle bump from a parallel universe that left a lasting bruise on our own. One speaks of the grand, lonely scale of our cosmos. The other hints that we are part of an infinite cosmic family. The truth remains hidden, a tantalizing secret whispered in the oldest light in existence. But the mystery itself is a gift. It expands our minds and soothes our souls, reminding us that there is always more to discover, more to wonder at. Thank you for joining me on this peaceful journey through space and time. If this exploration has brought you some measure of calm, please consider liking this video and subscribing for more lectures for sleep. And as you drift off, I leave you with a final thought to carry into your dreams. What do you believe the cold spot is? A vast and silent emptiness, or the first real evidence of a world beyond our own? Let me know in the comments below. Sleep well.